Oh, so here we go. We're going to try and do this best as we can. Uh, so I've got a PowerPoint. This is the book's PowerPoint that I use. So it's actually pretty good. We're starting, remember, and we starting in chapter 9 in your textbook. Um, so we're going to kind of follow with some of the examples. They use some of the examples that are in your e-text too that you can go through, and you can go through the e-text with that. We are in chapter 9. 9.1. So I'm going to share here on my screen. Let's see if we can get it here. Gonna share that. Okay, so if I remember this last year, I could do this. We're gonna go ahead and present this because I can actually write on this. So we're in chapter 9. Now, chapter 9 is the probability chapter, okay? And I'm going to be honest with you, this is probably the chapter that gets most people, but chapter 10 is not so bad. It kind of makes sense. So when it comes to test time and stuff like that, this is the one chapter that out of the whole semester, people have the biggest issues with, okay? And it's not one of my favorites either. And we talk about, wanting to be encouraging the kids on how to deal with things. So probability, and we know probability is, that 50-50 shot, that coin flip, okay? The odds on winning the lottery, which I heard a really cool joke the other day. It was a lady comes by and says, I guess it was anybody, says, we should play the lottery. And he goes, why? It was because you got a 50-50 shot. And he's like, I don't really think that's right. How can you get a 50-50 shot? She said, well, I'm either going to win or I'm going to lose. It's a 50-50 shot. So that's kind of the understanding we have with probability these days. Okay. And in a thing that's more like 13 million to 1, people think it's a 50-50 shot. Okay. So probability, and I hit that too much. Some of the things we're going to discuss, and unfortunately, some of these videos are going to be a little lengthy. I'll do my best to maybe make them a little bit better. So if I go too fast, stop the video, look at the screen, okay, and then rewind it, whatever the case may be. There's no problem doing that. So some of the things we're going to learn in the first section of chapter 9, how probabilities are determined, experimental opposed to theoretical, some of the few properties of probabilities, and then mutually exclusive versus non-mutually exclusive events, and also very, very little on geometric probabilities. This is going to show you a couple things, nothing heavy on that. Okay, hopefully I'll address most of the things that you'll see on homeworks and stuff. But your e-text will help you a whole lot on those too. So you can go to certain sections and help you out. So definitions, we're going to have some in this unit and almost every unit in this semester. So these are things we want you to be able to handle. Okay, learn these because, like I said, I'm working on trying to get an idea of trying to get you some extra credit, which I might just pull it into a Blackboard matching thing or something if I can work it out. I'm trying to figure out how I can do it and put it as extra credit to your test. So I'll try and keep that up to date with you. Okay. So, and it usually deals with definitions and stuff like that. But I'm a little concerned with it being you're not in front of me when you're taking it. So experiment. What's an experiment? An activity whose results can be observed or recorded. So we're going to do some sort of activity to be the experiment. An outcome is the possible results of an experiment. So if I was rolling a die, one die, okay, one die, your experiment of a die, you're going to have 6 outcomes, okay, 1 through 6. All right, sample space is a set of all possible outcomes for that experiment, okay? And then an event is any subset in that sample space, okay? So if I look at something like this, we talked about the die, right? So this is where I try to do my best impersonations. All right. So we talked about the die. The outcomes is 1 through 6, right? Okay. So your sample space would be 1, 2, 3, 4, 5, and 6. Okay. And to be a sample, we learned if you took 1350, a set should always have these squigglies. Hey, that's not a bad squiggly for computer drawing. Okay, so you're going to have, that would be your set. And an event would be any subset, such as 3 and 4. And that would be my subset. Okay, so all of those is things that we can deal with. Okay, all right, so let me get back out of that. Let's go to our next page. Suppose you have an experiment consists of drawing one slip of paper from a jar containing 12 slips. Okay, each has a different month of the year written on it. So 12 months, 12 slips. Find the following. What's the sample space S for that experiment? Okay, well, there's your list of all 12 months, and notice the sample space S, capital S for sample space, equals, and then they have the squiggly. You need to have the squigglies. If you don't put the squigglies, it's not truly a set. Okay, these are important. Okay, now out of that same set, the event A consists of the outcomes having a month beginning in June. Well, that's January, June, and July, right? So there should be 3 in event A. Event A is equal to set January, June, and July. Event B consists of outcomes having the name of the month that has exactly 4 letters. June, July. Anything else? Nope, just June and July. And again, the sets. Okay, event C consists of months having a month that begins with M or N. So we're looking at March, May, and November. And again, the set markings and capital C. Okay? So that's basic knowledge of that. Now, if we think about it, wouldn't, let's see here, wouldn't, let's see here, let's try and do this. Wouldn't C be a subset of S? Okay, C would have to be a subset of S because C here has 3 of the months that are in the month of all the years, the full year. So you would have C as a subset of S. Okay, give you an idea of all the terminology. Okay. All right, so well, I guess I need to clear all that before I can go to the next page. Oops. Let's get rid of this. Text. There we go. Yeah. Kind of remember how to do this. It's been a little while. All right, so you have 2 types of probability. You have what's known as experimental or empirical probability. We usually call it experimental, especially for the young kids. Okay, determining, and then you have theoretical. Okay, so experimental would be if you flip a coin 30 times and all 30 times comes up heads, then your experiment says it's a 1-in-1 shot. Okay, probably a bad example. Okay, theoretical is what it should be. Okay, so experimental is you actually do the probability and you give the actual data from the experiment. Theoretical is what it should be, which would be the outcome is ideal conditions. So if I flip a coin 1,000,000 times, I should be really close to half heads and half a million heads, half a million tails. Now, is it possible for you to flip it 1,000,000 times and get 1,000,000 heads? Possible. Very unlikely, but possible. And that would be your experimental probability. All right. So then you have equally likely, which is when one outcome is likely as another. So when you flip a coin, you're going to have equally likely outcomes. It's always going to be half, okay? And they're going to be a half for heads and half for tails. And a uniform space, don't use this one too often. Each possible outcome of the sample space is equally likely, okay? Now, when I gave you that example of 1,000,000 flipping the coins, that falls under the Bernoulli's theorem of large numbers. All right. So it says as the number of trials in the experiment increases, the experimental should get closer and closer to the theoretical. Okay. Which means the more you flip a coin, the closer and closer you should get to half heads, half tails. Now you can flip 10 times and get all heads, or 7 out of 10 heads, but you get to 100, you're going to be closer to a 50-50 shot. And the more times you do the experiment, the closer and closer to the theoretical you should be. Okay. Probability of an event will equally likely outcomes. This is for an experiment with non-empty finite sample. Okay. Sample space S with likely outcomes, the probability is, and all of this goes to say, how do I find probability of some set? It's the number of elements that you want over the total number of elements. Okay, so let S be a numbers 1 through 25. Meaning this is ellipsis, 3 dots means everything between 5 and 25. If a number is chosen at random, the same chance of being drawn with any other numbers, calculate each of the following probabilities. Okay. Event A has an even number is drawn. Okay. So if I want an even number is 2, 4, 6 all the way. So if you have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 12, 20, 22, and 24. How many even numbers are there between 1 and 25? That is 12 of them, okay? So there's 12 possibilities. Well, how many numbers are in the set, okay? So in the set, we have 25 numbers, okay? There's 25 total, okay? So the probability of drawing an even number is going to take this number, how many of them are there? There are 12 over the probability of the total, okay? Which would be 12 over 25, or 12 out of 25, excuse me, can't say it backwards. Okay, so I have a 12 and 25 chance of drawing a even if everything is equally. Okay, the event B, that is number less than 10 and greater than 20 is drawn. Well, which numbers are less than 10? Okay. So the numbers that are less than 10 are 1 through 9, and the numbers greater than 20 is 20 through 25. Now, what's the chance of you drawing a number less than 10 and greater at 20 and meaning at the same time? Okay, well, unfortunately that is no chance. The probability is 0. Why? Because you can't draw one less than 9 and greater than 20 at the same time. event C that a number less than 26 is drawn. Well, if I'm drawing one number, a number 1 through 25, and what's the chances of it being a number less than 26? Is 25 chances, right? And so I have a probability of 100%, 25 out of 25. Okay, so what do these mean? Okay, well, and I'm probably stepping ahead of myself, but I'll probably do that anyway. Okay, this, when you get a probability of 0, means it will never happen. If you get a probability of 1, it always happens. Okay, so those are specific ones that work. All right, the event D is a prime number. Now, there's a couple things I do want to talk to you about this, especially if you haven't had me in class before. Okay, so if we're talking about the events D that is a prime number, you have to know your prime numbers. The kids should know this before they do that. Okay, now a prime number, if you remember, does not start with 1. Prime numbers are 2, 3, 5, 7, 8, 9, 10 are not, 11, 12, 13, 14, 15, 16, 17, 18, 19, 19, 20, 21, 22, and 23. Those are your prime numbers up to 25. Okay, so we want to make sure you get all those. Oops. And how did I do that? Okay. So we go, let's get to the next page. So we have, these are your prime numbers. So there are 9 of them. So you're going to have a 9 out of 25 chance. And event E is both even and prime is drawn. Okay. Well, there's only one even number that's prime, 2. Okay. So if I look at that, I'm going to have only one possibility out of 25. So a very slim chance. Number that works over the total number. Okay, now we already talked about this, an impossible event, probability of 0. A certain event, gonna happen, probability of 1. Okay, now it says probability theorems, all based on if A is an event and S is a sample space, the probability of something happening has to be between 0 and 1. Okay, you can't have higher than 1 probability, you can't have lower than 0 probability, but it can be 0, and 0 means it never happened. 1 means it always happens. And the probability of an event is equal to the sum of the probabilities of the disjoint outcomes making the event. Okay, which means the following. If we draw a card at random from an ordinary deck of playing cards. Now, for a while in at least certain school districts, they went away from playing cards in probability. Playing cards are one of the best ways to teach probability, but you may have to teach some of your students what playing cards are like. Okay, what everything represents. What is an ace, like right here? They might not know what an ace is. What is a jack? What is a queen, a king? What is a club? What is a diamond? What's red? What's black? Okay, people don't know what a club is. They think it's a clover, okay? An ace is the A, right? So they may have to learn these things, and you have to make sure you understand that. For a while, a lot of kids didn't play cards, and so they stayed away from playing cards, okay? But if we think about that, you have to also understand that there are 52 cards in the deck, which holds 4 of everything. 4 aces, 4 twos, 3s, 4s, aces, kings, queens, jacks. That is an ordinary deck, standard deck. Okay, so these things the kids might have to know, may have to deal with them. But if there are 4 aces in the deck, the probability of pulling an ace at one time is 4 out of 52, which we always use the reduced value of 1 over 13. Your probability should always be in reduced form, never over 1, so you'll never have a mixed fraction. Okay, so What if we draw a card random from the ordinary deck? What's the probability that the card is an ace or a queen? So there are 4 aces and there are 4 queens, which means I'm going to have the grand total of that's 4 and 4, which is 8. There are 8 cards that can work here. So 8 over 52, that's an ace or a queen, probability of an ace or a queen, 8 out of 52, which reduces to a 2 in 13 chance, 2 out of 13. Okay? All right, mutually exclusive events. Events A and B are mutually exclusive if they have no elements in common. Okay, so if you have looking at 2 different events that have nothing in common, we give it this empty set. Okay, for example, consider one spin on the wheel. The sample space is 0 through 9, which, just FYI, just so everybody. I think I messed that up. I hope I'm still recording. I think I'm still recording. Let's hope we're still recording. All right, so I think I just stopped sharing. Okay, yeah, I'm recording. Okay, good. So when we talk about this, I wanted to get up here. I hit the wrong thing. All right, so this number right here, 0 through 9. 0 through 9 are 10 different things. People think they're 9. Kids will think it's 9 of them. But there are 10 things when you go 0 through 9. Okay, so if we say sample, the space of A is 0 through 4, and B is 5 and 7. Okay, so let's look at that. If I want to find if events A occurs, then B cannot occur. These are mutually exclusive. Okay, now because notice there's nothing in A that's in B and vice versa. Okay, so if A and B are mutually exclusive, which they are, okay, if I wanted to find them together or a union of them, I can add their probabilities together. The probability of a union of events such that any 2 are mutually exclusive is the sum of the probabilities of those events. Okay, so if I wanted to find the probability of, let's go back real quick, probability of A or B, I would actually, if I wanted to find the probability, let's do it this way, probability of A happening or B happening. Okay, well, I would have 5 out of 10 plus 2 out of 10, which would be 7 out of 10. Okay, so okay, so because they're mutually exclusive, I can add them together. Okay, 2 mutually exclusive use the union as a sample space. Okay, for example, consider the event A is 2 and 4. If tossing a 2 on a coin or 4, then the complement, so we're talking about complementary events. Excuse me, I had somebody come in my room. Okay, complementary events are going to be the opposite. So if I want to roll a die, 1 through 6, the probability of a 2 or a 4 is going to be 2 out of 6, or 1/3. Okay, the complement to that is everything that's not 2s and 4s, or 1, 3s, 5s, and 6s. Okay, so because the sample space is 1 through 6, probability of A happening is 2, 6, which means the complement of A would be 4, 6, and we would reduce those. Okay, so it's always going to be what's left over. If one has a probability of 6 out of 10, the other one would be 4 out of 10. Non-mutually exclusive. Okay, let E be the event spinning an even number. Well, how many even numbers do we have? 2, 14, and 18. Okay, well, how many total? There is 8. So the probability of E happening, and T is the event of spinning a multiple of 7, which is 7, 14, and 21. Okay, so since these are non-mutual, why are they non-mutually exclusive? Because they share the 14. Okay, let's make them non-mutually exclusive. Okay, so because they share something, you have to use this formula. You use the probability of E happening of the first event, you take the probability of the second event happening, and you have to subtract the intersection between the two. Now, what does that mean? Okay, so I'm going to hit the next button so I can explain it. This is what this means. Let me get into here. So the probability of E happening, 3 out of 8, which is these 3 out of 8. Probability of T happening is also 3 out of 8. Okay, but because they have this guy right here, this guy 14 happens in both of them, we have to account for that because otherwise we're double dipping. Okay, and so the double dip has to be taken away. So since there is one number 14, that's the intersection. Remember, again, if you haven't had 1350, you might not remember that that means intersection, that symbol. Okay, that's your intersection. That's what they have in common, right? Intersection. I'm going to try and spell it real fast. Okay, well, how many things do they have in common? They have the 1, so that's 1 out of 8. So then you add them up, subtract, and you get your final probability of all of this happening is a 5 out of 8. So you can't assume with the double dip in on there. Okay, so to sum things up, if you have the probability that's impossible is 0. If you have a probability of 1, that means it's always going to happen, certain event. Your probability has to be between 0 and 1. And if A and B are events and their intersection is no solution, then you add their probabilities. That makes them mutually exclusive. And if they're not mutually exclusive, you have to use this, where you have to subtract the thing they have in common. Okay, and there's some ways you can deal with that, as in some other kind of ways they deal. And then we have the complement. The complement of A is always going to be 1 minus the actual thing happening. Okay, so a couple examples to finish up on. Okay, a golf bag contains 2 red tees, 4 blue tees, and 5 white tees. Okay, so first and foremost, you have to know how many tees there are. There are a grand total of 11 tees. Okay, what is the probability that you pick a red tee? Well, there's 2 red tees out of a total of 11, so it's a probability of 2 out of 11. Okay, so going on with that, what's the probability of not R? Okay, so not a red. So there's 2 ways of thinking of this. So we'll go back. Okay, remember, there are 2 red tees, everything else is not. Okay, so if I wanted to go not red, I could go 1 minus red, which is 1 minus 2 11ths, which give you 9 11ths. Or you could just say, what's the probability of not red would be all the non-reds over the total. These are all, 9 is all the non-reds. So what is the probability of the event that a T is drawn random is either red or blue? Now there's nothing in common between, so it is mutually exclusive. Okay, so probability of a red is 2. Probability of a blue was 4. There were 4 blue tees. So I would take 2 over 11 plus 4 over 11, which is 6 over 11. Okay. Now, that's because they are mutually exclusive. And common objects are normally going to be mutually exclusive. Okay. And then the last part, really, I don't do a lot with geometric probability. This just gives you an idea of them that, besides, a fair coin is a 50-50, it's heads or tails. So this is using a square instead of a circle or, something like that. But they have to be equally in both ends. And then a die is 6 parts. Okay, so you could use a hexagon if you wanted to instead of a circle. And that's just same ideas. Okay, so hopefully, we'll stop sharing. Hopefully that will help you enough through there. Again, by all means, use your book. They have some videos in the book also, I believe, on the e-form. If you have any other issues with it, make sure you come into my office. Okay, we will see you later.